to Educator.com. In today's lesson, we're going to continue on talking about matrices, this time focusing on two special types of matrices, identity and inverse matrices. The identity matrix is a square in a square n by n matrix, which has 1 for every element in the main diagonal and 0 for every other element. So an identity matrix is a square matrix, and let's look at an example. For example, a 2 by 2 matrix, that's an identity matrix. It says that this has 1 for every element in the main diagonal. So that's 1 and 1, and 0 for every other element. Okay, looking at another example of this for a 4 by 4 matrix. So in the main diagonal, that'd be here, I've got all 1s. And I'm going to fill in the other spots. With 0. So down the main diagonal I have 1s, everything else is a 0. And this is 1, 2, 3, 4, 1, 2, 3, 4. So it's a 4 by 4 square matrix. Now, let's talk about properties of these matrices. For any n by n matrix A, if you multiply that matrix times its identity matrix, then you will get the original matrix back. And you can also multiply these in either order. So, in a way, you can, when you think about identity, the identity property of multiplications, think back to regular numbers. And when we talked about identity with multiplication, we would say that if you multiplied n, a number n, any number, times 1, you got that original number back. And that was the identity property with multiplication. For example, if I took 3 times 1, I'm going to get 3, or 10 times 1, I'll get 10 back. This is the same idea, but with matrices. So this functions the same way as 1 in this case, because if you multiply the matrix times its identity matrix, then you will get the original matrix back. The same way as if you multiplied a number times 1, you get the number back. So let's go ahead and try this. And remember that unlike 1, though, there's just the number 1. But for identity matrices, there are multiple ones. You see that for a 2 by 2 matrix, the identity matrix will be different than for a 4 by 4 or a 3 by 3. Okay, so let's use this 2 by 2. And let's say I had some matrix A, and it's going to be 3, -1, 2, 5. And I'm going to multiply it by its identity matrix, which is going to be this one, because it's a 2 by 2. And let's see what I get. Well, recall that for multiplication, that if I'm going to look for this position, row 1, column 1, row 1, column 1, I'm going to multiply row 1 of this first matrix times this first column here. So that's going to give me 3 times 1. And then I'm going to find the sum of those products. 3 times 1 plus -1 times 0. So that's going to give me 3 plus -1. Excuse me, 3 plus 0, or 3. Okay, so I'm going to get 3 up here. And let's look for row 1, column 2. Row 1, column 2 will be row 1, column 2. So 3 times 0 plus -1 times 1. So this is going to give me 0 minus 1. 0 minus 1 is -1. So -1 goes right here. And continuing on now to the second row, row 2, column 1. Row 2 of A times column 1 of the identity matrix is going to give me 2 times 1 plus 5 times 0, which is going to equal 2 plus 5. 2 plus 0 is 2. 2 plus 0 is 2. Okay, then finally, row 2, column 2. This is going to give me row 2, column 2. So row 2 here, column 2 here. Row 2 is 2 times 0 plus 5 times 1. Well, that's simply 0 plus 5, or 5. So you see that this property is shown here, that if I have a matrix A, and I multiply it by its identity matrix I get A back. The same way for numbers, if with the identity property of multiplication, if I take a number and multiply it by 1, I get the original number back. Okay. Now, talking about matrix inverses. If we have two n by n matrices, so these are square matrices, and we say that they are inverses of each other. So if I have two n by n matrices A and B that are inverses of each other, if AB is equal to BA and that product, AB, is equal to the identity matrix. So if A and B, the product of A and B, turns out to be the identity matrix, then those two matrices are inverses of each other. And the inverse of A, if it exists, and we're going to talk about that in a few minutes, that it may not always exist and why, is written as A inverse. We pronounce this A inverse. Okay. So again, if I'm not, let's say I was given two matrices, A and B, and then I was asked, are they inverses? The way I would determine that is by multiplying those two out, and if the product is the identity matrix, then they are inverses. If it is not, then those two are not inverses of each other. So let's talk about finding the inverse of a 2 by 2 matrix. So if we have some matrix A that looks like this, the inverse of A, if it exists, is given by this formula. A inverse equals 1 over, and if you look at this, AD minus BC, this is going to look familiar, and that is the determinant of this matrix. So remember that the determinant of a 2 by 2 matrix is given by the formula AD minus BC. So it's 1 over the determinant times this matrix. And it's pretty easy to remember how you form this matrix if you just look at it this way. The way I got this is I switched the positions of A and D, and then I took the opposite sign of B and the opposite sign of C. So if I had numbers here, let's look at that. If I was told that A is the matrix 3, 4, 1, 2, and I was told to find A inverse, well, then I would take 1 over the determinant, which is 3 times 2 minus 4 times 1, times, now to find this matrix, I'm going to switch these positions. I'm going to put 2 here and 3 there. I'm going to take this number and I'm going to keep the number, but I'm going to put the opposite sign. If this was a negative 4, I would have made it 4. Same for C position. I'm going to keep it 1, but I'm going to make it the opposite sign. Now, stopping here for a second. I mentioned that if the inverse exists. Looking at this, you can see that there could be a situation where the inverse does not exist. Okay, here I have 1 over 6 minus 4, so that's 1/2. Well, that's allowable. But if this had been, say, 6 minus 6, that would have been 0. That's not allowable. That's undefined. So I wouldn't have been able to find A inverse. Okay? Therefore, there are situations, and it's when this denominator turns out to be 0 that you can't find the inverse. So it's a good idea to look for this denominator, right away before you do any more work to determine if you even can find the inverse so you don't waste any more time looking for something that does not exist. Now, now that I've found that this is 1 over the determinant is actually 1/2, I can just multiply using scalar multiplication. This is functioning as a scalar to figure out A inverse. So I'm just going to multiply 1/2 times each element. 1/2 times 2 is 2 over 2, which is 1. And 1/2 times negative 4 is negative 4 over 2. That's negative 2. 1/2 times negative 1 is negative 1/2. And then 1/2 times 3 is 3/2. Now, if you wanted to check your work, you could always check your work by taking A times A inverse and seeing if it comes out to the identity matrix, which it should if you did things correctly. So if I were to take 3, 4 times 1, 2, and then multiply it by 1, negative 2, negative 1 half, 3 halves, I would find that it does come out to the identity matrix for these 2 by 2 matrices. Okay. So, first we're asked in example 1 to determine if A and B are inverses of each other. So, are A and B inverses of each other? We're given these two matrices and asked if they're inverses. Well, recall that if two matrices are inverses of each other, then if I multiply them, I can actually multiply them in either order, and I'm going to get the identity matrix. So before I proceed, let's just think about what the identity matrix is for a 2 by 2, and I'm going to have 1 along the main diagonal and 0 everywhere else. So this is the identity matrix in this situation. I'm going to go ahead and multiply these and see what I end up with. Okay, doing some matrix multiplication. First, row 1, column 1. First row, first column. That's 0, 0, 0 times 0, plus 1 times 1. And that's going to give me 1 in this position. Now, row 1, column 2. Row 1, column 2. 0, 0, plus, okay, then that would be 1 times 2. So row 1, column 2. I did 0, 0, now 1 times 2. That's 0 plus 2, so that's 2. So this position, I'm going to get 2. Now, row 2, column 1. Okay. Row 2, column 1. 2 times 0 plus 1 times 1. That's going to give me 0 plus 1 is 1 right here. Row 2, column 2. Okay, so row 2, column 2. 2 times 0 plus 1 times 2. 0 plus 2 is 2. All right, so the question I was asked is if these are inverses of each other. Well, when I took their product, I took the product of A and B, I found that AB does not equal the identity matrix. This is not the identity matrix, this is. Therefore, are A and B inverses of each other? No. A and B are not inverses of each other. And I was able to check that using this property. Find the inverse if it exists. So finding the inverse of a 2 by 2 matrix, recall, uses this formula. 1 over the determinant, which is AD minus BC, times the matrix D, negative B, negative C, A. Okay, so A inverse, calling this matrix A, is 1 over the determinant. Here I have 1 times 4 minus 2 times 3. And just looking at this quickly, I see that this is 4 minus 6, so that's negative 2, and therefore that inverse, that's negative 1 half, so this inverse exists. I didn't get 0 down here before I proceed any farther. Times, okay, dA means I'm going to switch these two. 4 is going to go in the A position, 1 will go in the D position. For B, I'm just going to take the opposite sign, and for C, I'm just going to take the opposite sign. Okay, proceeding. This is going to give me 4 minus 6, as I said, which is going to give me negative 1 half, times 4, negative 2, negative 3, 1. Now I need to multiply each element in here by negative 1 half, and that is going to give me negative 1 half times 4, which is negative 2. Negative 1 half times negative 2 is negative 2 over negative 2, which is 1. Negative 1 half times negative 3 is going to give me positive 3 halves. And negative 1 half times 1 is negative 1 half. Okay, now if I wanted to check this, I could check it by saying that A times A inverse is the identity matrix. So this is A inverse. Let's go ahead and multiply this times A and see what happens. Okay, so let's try A times A to the negative 1 and just see what we get. So here I had A, that's 1, 2, 3, 4, and A inverse. And that is negative 2, 1, 3 halves, negative 1 half, equals, okay, working over here, row 1, column 1. That's 1, and I'm going to just go ahead and do part of this mentally. 1, row 1, column 1. 1 times negative 2 is negative 2. 2 times 3 halves, well, 2 times 3 halves, this cancels out, that just gives me 3. So it's going to give me negative 2 plus 3 equals 1. So I get 1 right here. Okay, row 1, column 2. Row 1, column 2. That's 1 times 1 is 1. 2 times negative 1 half is negative 2 over 2, which is negative 1. So that's 1 minus 1, that's 0. 0 goes in the row 1, column 2 position. Let's go on to row 2, column 1. Okay. Row 2, column 1. So this is row 2, column 1 is going to give me 3 times negative 2. That's negative 6. And then this is 4 times 3 halves equals 12 halves. That equals 6. So negative 6 plus 6 equals 0. So I get 0 right here. Row 2, column 2, last position, equals row 2, column 2. 3 times 1 is 3. 4 times negative 1 half would be negative 4 halves, or negative 2. 3 minus 2 is 1. So you see, I actually did get the identity matrix. So I figured out A inverse, and I was checking that I was correct by saying, well, if this truly is the inverse, when I multiply these two together, if those two matrices are inverses of each other, I'll get the identity matrix. And this is the identity matrix for a 2 by 2 matrix. So the inverse, the answer to the question that they're asking is this right here. However, I checked my work right there. Okay. Example 3. Find the inverse if it exists. Using my formula, A inverse equals 1 over the determinant AD minus BC times switching D and A and changing the signs of B and C. Okay, so A inverse equals 1 over, this is AD, that's negative 1 times 0, minus BC, minus negative 3 over, or excuse me, times negative 1. Okay, then times this matrix were found by switching these two positions, 0 and negative 1. Now, for negative 3, which is in the B position, I'm going to take the opposite sign. That's going to be 3. For negative 1, which is in the C position, I'm going to take the opposite sign and make it 1. Okay, let's make sure that this is going to work now. This is 0 minus negative 3 times negative 1 is going to give me 3. So that is 1 over 0 minus 3. And that there will be an inverse because this is not 0. If this had come out to be 0, I couldn't have found the inverse. It's negative 1/3. 0 minus 3 is negative 1/3. Times this matrix. Okay, this is going to give me, if I multiply negative 1/3 by each element in here, I'm going to get negative 1/3 times 0, and that's going to give me 0. Here, I have negative 1/3 times 3. That's going to give me negative 3 over 3, or negative 1, right here. 1/3 times 1 is 1/3, and 1/3 times negative 1 is negative 1/3. Okay, so again, I was asked to find the inverse. I used this formula. I first found the determinant, and I determined that it was negative 1/3. Therefore, I could find the inverse. And then I multiplied it by the matrix, which consists of switching the positions of these two and reversing the signs of these two. This becomes a positive, this also becomes a positive, giving them the opposite signs than what they had. Then I multiplied negative 1/3 by each element in this matrix to get this. And if I were to check it, which I could, it would be by multiplying A, the original matrix, times its inverse, and I would find that I get the identity matrix back. Okay. Find the inverse if it exists. Again, recalling my formula, A inverse is 1 over the determinant, AD minus BC times the matrix found by switching A and D and reversing the signs on B and reversing the sign on C. Okay, so first the determinant, that's 1 times 6 minus 2 times 3. The matrix, switch these two positions and reverse the sign on the 3 and reverse the sign there. Now, you probably already saw I didn't even need to go that far because there's a problem. What I have here is 1 times 6, which is 6 minus 6 times this matrix. Well, this turns out, obviously, to be 0. And since you can't have that, that is not allowed, it's undefined, we can stop right here because this is undefined. In this case, inverse does not exist. And the clue is, as soon as you see that you're having to divide by 0, you know you're not allowed to do that. You're not allowed. So the inverse does not exist. That concludes this lesson on educator.com on identity and inverse matrices, and I will see you again soon.